form a partial differential equation from a given system of curves. Okay, so broadly there are two types of system of curves. In one type, whatever we are discussing at first, so these are this is a type where there are some independent variables, one dependent variable, and some arbitrary constants involved. And there is another which exactly same, one dependent, more than one independent, but instead of arbitrary constant, there may be arbitrary functions. Clear? Instead of a1, a2 up there f1, f2 up to fm. Okay, so let us consider a system of curves, whatever it is given by the equation capital F of this. You can see this. There are how many independent variables? x1, x2 up to xn, n number of independent variables, z is dependent, and a1, a2 up to am, these are arbitrary constants. Okay, so depending on the values of n and m, we have the following possibilities. Number one possibility, n could be equal to m. Okay, this is one possibility. Then how to, what is our target? A system of curves are given. Okay, so we have to form a partial differential equation whose solution is that system, whose solution represents that particular system, whatever we start with. Clear? Okay, so that is our target. Okay, by the way, I like to ask you whether you know regarding formation of partial differential equation or not. Please, any one of you responds whether you know partial differential equations, how to form partial differential equations.
So only on a very basic scale, sir, not very well.
Okay. But by any chance from up to 10+2 syllabus, it was not there. Only formation of ordinary differential equations.
No,
Possibly.
sir, no, sir. Only formative formation of ordinary decimal, no partial.
Okay. So I have to start with all that basics things. Okay. Someone raise Ram Sharma. You are talking to, you want to say something? Okay, so what is our target? What is given? First we have to see what is given. We are given a system of curves where there are a m number of arbitrary constants involved. We have to find arbitrary constant in terms of the partial derivatives, and then we are done. Clear? Okay, so whatever the differential equation we should get, that differential equation, partial differential equation, should not involve any arbitrary constant. Clear? So we have to eliminate arbitrary constant, that is for sure. Okay. So the PDE can be obtained by just eliminating a1, a2 up to am from the relations. So this is one relation. Another relation is del f del x1 equal to 0. Number 3 del f del x2 equal to 0. In this way we get del f del xn equal to 0. So ultimately whatever we are getting a PDE This PDE's order will be 1, and okay, you see, we will get unique partial differential equation whose order is 1 in this case particularly. I think you understand, because n equal to m, number of independent variable is exactly equal to the number of your arbitrary constant. So only we have to differentiate the function or the system with respect to all possible independent variables, means there are n number of variables. So for each of the cases we are getting one equations, and then definitely if we eliminate it with the help of the given system of equations, so we'll get the value for a1, a2 up to an, because m equal to n in this case. So definitely what we get, we can replace ai's in terms of the partial differentiation, first order partial differentiation or first order partial derivatives, so that ultimate equation, whatever the equation we are getting, that is a partial differential equation, which is a first order partial differential equation, and that is unique. Okay. Give examples. First, we see the possibilities. Another possibility is number 2. If your n is greater than m, that means number of independent variables are more than that of your arbitrary constants. So in this case, elimination of arbitrary constant usually give rise to more than one partial differential equation of order 1. You can hear me? Hello?
Yes, sir. Yes, sir. Yes, sir.
Yes, sir.
But Ankita, I like to ask you, in this case, if we see the previous one, so we can do del f, del x1 like this. This we can do, f equal to 0, this is 1, and then del f, del x1 equal to 0 equal to del f, del x2 in this way up to del f, del xn. Clear? So but n is more than m. Then in this case also, is it possible to get a first order partial differential equation from here or not? That is my first question. And if it is yes, then whether it is unique or not. What you feel? Rajata?
Sir, it will not be unique, sir. It will be rather there will be multiple forms, because if there are more independent variables, that would, like, if I
That
would
would give us more number of equations. Clear?
exactly, sir. Exactly.
Okay, then it is not unique.
So we cannot eliminate all the arbitrary constants. That's it.
No. We can eliminate. We are having the equations more. Then we can eliminate, but in a different pattern we can eliminate. So whatever the differential equation we will be getting, it is not unique. So your answer and my answer maybe is different. Okay. So order 1, this is also correct. There is no ambiguity on that. It is also correct. Clear? Because no need to go for the higher order partial differentiation. We will very easily eliminate all the arbitrary constants which are lesser in number than that of the independent variables. So we are getting more number of equations from here. So definitely we will get a partial differential equation which is of order 1, but it may not be unique. Okay. Then what could be the last possibility? Number 3 possibility.
M greater than n.
n is less than m, means number of arbitrary constant is more. So in this case, what we have to do? Can we just
eliminate arbitrary functions?
Yeah, again we have to eliminate arbitrary constants, that is for sure, because
No,
in
functions,
this
sir. Functions, sir. Eliminate arbitrary functions.
No, arbitrary constants, because we are just dealing with only arbitrary constants. You see, these are arbitrary constants. These are not arbitrary functions. Okay. So what I said, that suppose this is a system of linear system of equations or system of curves where one dependent variable z is there, this z is there, and n number of independent variables x1, x2 up to xn are there, and there are m number of arbitrary constants involved in that system. Because the constants are arbitrary, that is why this is a system of curves. Clear? So from the given system of curves, we have to find a partial differential equation whose solution is that system of given curve. Clear? So that is our motto initially. And depending on the values of n and m, we have the following possibilities. First possibility was your n equal to m. Second was n is greater than m. Third one is just reverse. What is n is less than m? Clear? Okay, so again here also we have to eliminate arbitrary. We have to eliminate arbitrary constants ai's from f equal to 0, del f del x1 equal to 0 up to del f del xn equal to 0. See, here whatever we are getting, only for this particularly there are n number of equations. Clear? But that n is less than the number of arbitrary constants, so definitely we are not in a position to eliminate all the arbitrary constants. Clear? So we need to go for the higher order partial derivatives. Understand?
Yes, sir.
Okay, so we need to create more number of equations in order to match it. So we have to go beyond that.
Okay, sir.
Okay, so this will be del 2 f del x2 x1 2 equal to 0, del 2 f del x2 2 equal to 0. In this way, del 2 f del x1 x2 del x2 equal to 0, and so on, whatever it is necessary depending on the situation. Suppose your n is 2, m is 3, in this case up to second order we have to go for. Okay, now I think it is clear to everybody. Okay, so it depends on the values. So we'll be getting a partial differential equation whose order is more than 1. So we'll be getting a partial differential equation whose order is greater than 1 and may not be unique, because here we can have more number of equations also, because you can find maybe del f del x 3 2 in this way, del 2 f del x 3 2. In this way you can create more number of partial differential equations, sorry, partial derivatives, so that bring to different kind of partial derivative, but order would be same. Yeah. Okay. Okay, so let us concentrate on some examples. It will be more clear. Example number 1. If I take x minus h square plus y minus k square plus z square is equal to a square, where your h, k, these are arbitrary constant. Okay, a is a constant, so a is not important. This is a constant. These are arbitrary constant. X, y is what? Independent variable, and z is dependent variable. Sure. So this is a system of curves where z is the dependent variable, x and y are two independent variables, h and k are arbitrary constants. So in this case, what should be the differential equation, partial differential equation? Its order. Okay, first let me tell why whatever the differential equation will get, that is a partial, not an ordinary differential equation. You can say
because z is dependent on two variables.
two independent variables. Yes, yes, yes. Very good. Because here number of independent variables is more than one and dependent is one. Okay, that is why we whatever the partial differential equation we will get, that is of course for this is a partial differential equation. Okay, so if we differentiate with respect to x, what is del f? Suppose this is your f. F
Sir?
is equal to yes.
So the above equation is a equation of sphere, 3D sphere.
Yes. What is fx? Yes, yes, you are correct. Not just equation of sphere. This is a collection, like a system of equations of sphere. Okay, if you change your h and k, your equation of sphere will be changed. Clear? Fx is 0. From this, what we get? Twice you.
Homogeneous.
Okay, let me please tell what is this. So y minus k, so there is no x involved here. This will be what?
0.
0.
And z, twice z, zx. And right side will be 0. A is a constant. So ultimately whatever we get, that is x minus h will be minus z, zx. This is your equation number 1. Okay, maybe this is your equation number 2. And what could be your equation number 1? This is, okay, given equation. Now fy is 0. What could be this? This gives us y minus k is equal to minus twice z, zy. Clear? This is equation number 3. So whatever we can write, putting x minus h and y minus k in 1, we get what we'll get. Okay, let's check what it is. Square. Okay, square z square equal to a square. Its square means this is z square zx square plus here again z square zy square plus z square is there is equal to a square. So this is your partial differential equation. So whatever we can write, z square common, zx is normally p, that is p square plus q square plus sorry, this is plus 1 is equal to a square. This is your given PDE. Okay, so we are done. What could be the order of this partial differential equation? What could be the order of the partial differential equation?
Sir, it's first order.
First order.
Very good. First order. Is there any possibility of getting order more than one? No, because here whatever the number of independent variables and number of arbitrary constants are what?
Same.
So that is why we will get order of the differential equation is 1, and this differential equation is unique. In fact, if you try in a different way, there is one question. We supposed to find the value for h in terms of maybe partial derivatives, and k in terms of partial derivatives or dependent variable, independent variable, etc. Clear? And we have to put the values, but we do not do like that way. We did what? X minus h in terms of that. So because x minus h is in the given equation, you see x minus h, y minus k, so that it is easier to find if we put x minus h form. Okay, so that will be easier. Next, come to the example number 2.
Sir?
Okay. Yes, please.
Sir, y minus k equals to 2zzy. So squaring it would be 4z squared zy. So 4 will be there.
Okay, so sorry, and there is a mistake here because both side 2 is there, so it will not be 2. This is just clear. Like in this case, 2, 2. Because y minus k square is there, so if you differentiate with respect to y, so 2 into y minus k will be there in the left hand side. Similarly, in the right hand side, if we move it to the right hand side, it will be 2z zy. Understand? Now you can see the corrected version. Okay, if your question is like this, z is equal to ax plus y, a is arbitrary constant. Can you form a partial differential equation?
Yes, sir.
Yes, sir. It will be possible, but since there are two dependent variables and only one arbitrary constant, it means n is greater. It
Won't
means
be
n is
unique.
greater than m. So
Okay,
won't
so
be
we
unique.
will on be unique. So one possibility, we like to find two possibilities. One is zx is equal to a. So this, if we put it, this is your number 1, because only a we have to find. So z is equal to zx x zx plus y. So this is your one PD, one possible PD, and zy is particularly equal to 1 here. So can you say this is also a PD? There is no arbitrary constant involved. This is another PD. Can we say yes or no?
no, sir.
No. differentiate this thing with respect to y partially, then in the left hand side it will be z y, in the right hand side it
Yes,
will be
yes,
1
yes,
only.
yes, 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 yes.
So look at this partial differential equation. This is already a partial differential equation, but it is without any arbitrary constant. So this is again a partial differential equation. So we see that the partial differential equations are not unique here, but order is 1, of course. Understand? So this is of category 2. Next, okay. If I give another example, example number 3, whatever it is, ax square plus by square plus cz square is equal to 1. In this case, a, b, c, these are arbitrary constant, and x comma y, these are independent variable, and z is dependent. Clear? Okay. In this case, what we can find from here?
So the order will be greater than 1.
Yes. Okay, let us find for that, because number of arbitrary constant is more than the number of independent variable. So what we will get, this is first one is ax plus cz zx is equal to 0. That means a by cx plus zx is equal to 0. This is your 2. This is particularly your 1. Next, if we differentiate partially with respect to y, what we get? Similarly, b by c y, just I give step jump, plus z y is equal to 0. This is your 3. Clear? If we differentiate partially with respect to y, what we get? First, we like to differentiate with respect to x again. So a by c plus this will be zxx plus chain rule I use, then zx its square is equal to 0. This is your 4. And if I differentiate partially with respect to y, then it is b by c plus zyy plus zy square is equal to 0. This is your 5. So we get a by c, b by c, then we can find. Okay. So we can put a by c is what? X into a by c. What is a by c? This thing. So minus of zxx plus zx square plus zx is equal to 0. That means what we get? Minus x zxx plus sorry, not plus, this will be again minus x zx its square plus zx is equal to 0. So this is your partial differential equation whose order is 2. Okay. So ultimately I can make it next line, I can make it minus, these are plus. So it looks nicer. Xz xx plus x zx square minus z into zx is equal to 0. So this is your partial differential equation whose order is second. Can you find any other? Yes, if you can put b by c in this equation. If you put b by c in this equation, you will get another. Okay. So in this case, what we see, order of the partial differential equation is more than 1, but the partial differential equation is not unique. Clear?
Yes, sir.
Okay. Then in my lecture note, you will see there are several other exercises, so you can solve those exercises. Okay. So there is still another type of formation of partial differential equations by eliminating arbitrary functions. So we can consider u and v are functions of x, y, z, where z is a dependent function, dependent variable of the independent variables x and y, and we assume that another type B formation of PDE by eliminating arbitrary functions. So we just assume phi u comma v is going to be equal to 0 for phi an arbitrary function, and u and v, these are functions of x, y, z, and these two independent and this is dependent as usual. Okay. So what we have to do here, we have to partial differentiate with respect to u, and you have to apply the chain rule. Then we will get one equations like that. Okay, we like to use the chain rule. So del phi del u, so it will be ux here plus uz, because it is a function of x and xyz and zx, plus there is still another variable, so del phi del v into vx, it will be plus vz and zx. This is 0. I think you understand the chain rule. So in case of your partial differential equations, whatever we will do from now and onwards, most of the times we have to use chain rule of differentiation. Clear? Is there any ambiguity here?
Sir,
I
could you
like
repeat
to,
once again, sir? So could you repeat it once again, sir?
yeah. See, phi is a function, arbitrary function. It is a function of two variables, u and v. We have to think about the variable and its nature. U and v are two variables, and phi is an arbitrary function which is depending on u and v. And at the same time, u and v, these are functions of x, y, z, where x and y are independent and z is dependent. Clear? So you see the involvement, one arbitrary function, two variables which are again dependent on x, y, z, and again z is dependent on x and y. So ultimately, if we go from lower to upper, so x and y initially two independent, z is depending on x and y, and u is a variable, dependent variable or functions of x, y, z. Similarly, v is another functions of x, y, z. In fact, these two functions are again a variable, and this is connected by an arbitrary function phi of this. Okay, so this is a given. This is a given thing. This is entirely your by means of an arbitrary function. This is okay. So in case particular case, we have to see the whatever examples will come, we will do accordingly. This is the main process. Okay, now look at if we want to differentiate partially with respect to u, because there are two variables initially, u and v. So del phi del u. So again, u is a functions of x, y, z. So here we have to do ux plus uz, because z is again independent variable, sorry, dependent variable, that is why again zx. Okay, so ux, no need to do xx because x is independent, so no need to do that. Okay, this part is clear. Similarly, phi is a functions of v also, so we have to partial differentiate with respect to v. Del phi del v, here it will be vx plus vz zx. Clear? Okay. So
Sir, you wrote VZ, sir, and UZ, sir. It should be UX, I guess.
why it should be ux?
So how are you partially
ux.
different?
This is ux. There is no problem on that.
No, so how is the UZ coming? Because how do you partially differentiate with respect to a dependent variable?
No, no, no. U is a function of three
Oh,
variables, na
acha,
x.
acha,
So
acha, हाँ, you can be
that is
differentiated with
why.
respect to Z. Acha, acha.
Yeah, yeah. Okay.
Okay,
Since
sir.
z is again, we have to think, since z is a dependent variable of two independent variable x and y, that is why this term is coming zx. Uz zx. Okay.
Yes, sir.
Okay. So whatever we can write, if we simplify it, phi u divided by phi v, this will be minus vx plus p vz by ux plus p uz. Okay, what is your p? P is equal to zx. Okay, natural meaning. Small p, small q, these are the notation for zx, means del z del x, q for del z del y. Okay, so whenever z is your dependent, x and y are independent, then we can use small p q. There is no problem because there is no ambiguity. But if your given system z is a functions of say for example x and t, then we cannot use p. Okay, so we have to be cautious here. Understand? Where we
Yes,
can
sir.
use p, q, r, s, t. These are these things where whatever our very standard phenomena happens, means z is dependent, x and y are independent, then we can use those standard symbols. Okay. Still, another way of differentiation is there. We can differentiate partially with respect to y. So what happens? This is phi u partially differentiate with respect to y gives us phi u by phi v is equal to minus, it will be vy instead of vx, plus it will be q vz will be same, and this in the denominator it will be u y plus q uz. Okay, so this is your number 2. You can say this is number 3. Number 1 is the first one. Okay, so we can say from 2 and 3, we can say these are same, is not it? So ultimately we can get the differential equation. These are same. These things means Vx plus P Vz divided by Ux plus P Uz is equal to Vy plus Qvz divided by what is Uy plus Quz. So this means what? This means basically some P plus something Q. This is basically your this is equal to some R is common. Okay, so this is your partial differential equation. And what it is, you can see this thing is particularly Uy Vz minus Uz Vy. This is similarly, this is Uz Vx minus Ux Vz. Okay. So in this case, how to do, you understand. So in the next class, I will give some more examples regarding arbitrary functions so that it will be very clear to you all. Okay, this much for today.